All right, here we go again. So last time we were working on this grammar utils library that I'm trying to get into a good state. And we had written this block of code for calculating what I call the first follows graph on our for our grammar. And I didn't feel like I did a very good job explaining what I meant by this graph. So we're going to go ahead and go into a little bit more detail, see a bunch more examples, and we're again going to just try and follow the code and understand how this works. But also, I had ported a bunch of the tests that I had, so now rather than just having the 1 or 2 tests that I coded up in the last example, I have ported over a bunch of pre-existing tests that we ran, so we can see that this code in fact does work for a number of cases. We will go through a handful of these to see how they work. So the first, I want to say the easiest example would be understanding how firsts work. So we're gonna just kind of copy these over to our whiteboard here. And walk through the example. So this first grammar, lines 94 to 99 here, we're going to have two simple rules, a to x and a to y. And we want to calculate the first of the non-terminal a. Again, the first is the set of all terminals which, when you expand the non-terminal following any of the rules in the grammar, eventually the expansion will lead to a string of non-terminals, or a string of terminals, and the first is the set of terminals that appear at the start. So what that is going to look like in this case is calculated like this. So we want to know what the first of a is. There are two rules. Either we're going to have a expand into x, or we can have a expand into y, and in either case we should just get it's so trivial it's hard to even write it down. This is just going to be the set x comma y, and the way that we calculate that is by mechanically is we look through each of the rules where the non-terminal that we're searching for the first of is the left hand side, and then we're going to look and see what the first symbol is on the right hand side. If it's a symbol, then it's just going to go into the set. And so for the second rule here, we're going to do the same thing, and that's going to go into the set. So that one is the test first. It's sort of the simplest possible case. So we're going to go and look for one that is a little bit more nuanced than that. Here is a more nuanced one. So test first 2 here. We're going to have A goes to B. We're going to have B goes to C. We're going to have C goes to D, Y. And we're going to have D goes to X. And we're going to have D goes to the empty production. We'll just call it epsilon there. That's this one down here. And what we want to do is calculate the first of our non-terminals. So let's actually start off with the bottom here. The first of D is probably the easiest. So when we want to calculate the first of D, we're going to look for all rules that have D as the left-hand side. And then we're going to look at the first symbol on the right-hand side. Now what's a little thought here, this epsilon is actually not a symbol. This is a, remember this is written in the notation. This is actually an empty list, and over here this is a list with one element. Since this is the empty list, the first of D, this rule is not considered for calculating the first of D. We only get this element here, and we get x. So this is where my formulation is different from how a lot of textbooks would work, where you would throw an epsilon in here even though it's not really a symbol. I don't like that because epsilon is not a symbol. It breaks sort of a basic principle of the idea that the set is actually a subset of terminals, but epsilon, the empty string, is not a terminal. So we're not going to put that in our definition. Just know that a bunch of textbooks will add an epsilon in here, and I think that's hot garbage. So the first of D is just the set containing X, and that's the easy one over here. We're going to throw that up there. The first of C is going to be a little bit more interesting. So the first of C means that in order to calculate the first of C, we are going to look at all rules that have C on the left-hand side. So that's the only rule with C on the left-hand side. We're going to look at the first symbol, D, here. Now, this symbol, if it were a non-terminal, we would throw it into the set like we did last time. However, it's not, or sorry, if it's a terminal, we would throw it into the set, but it's not a terminal, it's a non-terminal. And so we actually can't add that to our set directly. Instead, what we do is a kind of recursion. So you can imagine if you have a symbol C, you can replace C with, we'll use C can be replaced with D and Y, but then in the production this is going to get replaced again. There's actually two ways to move forward with it. Either it's going to be replaced using this rule here, and that's going to give us XY, or it's going to be replaced with this rule here, in which case it's going to be an empty string followed by Y. So we're either going to get one of these two strings in the end, and the first terminal that we see among these is X and Y. So intuitively we know that the first of C is going to be X and Y. So we'll keep that in our back pocket. But let's see how we actually, so let's put quotes around this because this is sort of our expected test. And sure enough, that is what the test says. The first of C is X and Y. Let's throw this over to the side and see how we actually calculate that in practice. So again, starting from scratch here, the first of C, we're going to look at all of the rules that have C on the left-hand side. We're going to look at the first symbol. Since this is a non-terminal, that means that we're going to sort of absorb the first set of D. But it's going to be more than just that, because the first set of D, if we look at that, we just calculated this up here. That's just X, and so we see there's a discrepancy between these two things. Let me get my symbols in the right place. There we go. All right. So we see there's a discrepancy. It's not just first. It's going to be first and something else. We're going to use the mathematical U notation to denote the union of two sets. So it's going to be the first of D unioned with something else. Well, unioned with what? Well, sometimes D disappears due to this rule. And so the general rule when we're considering the first set added by a rule like this is we go down the line. We first see this non-terminal and we add the first of D. We add the first of that non-terminal. But because D is nullable, we are going to actually repeat the process, go down the line, and check the same thing over here. We're going to see that Y is next in line. So in the event that D expands to the empty string, then we're going to consider Y, and that's why we're going to union it with the singleton set Y. Let's see where this is in the algorithm. So here we're calculating the firsts, and we see the case we see the case down here to begin with that we're going to look at each symbol on the right hand side. The first symbol, that D, we saw that it was a non-terminal, and so we are going to add this first of D here, and that is going to be this line here. This link is really saying that I'm adding that set, I'm unioning that set with the rest, with a bunch of other things, and that's going to become first of C. And then after that if statement, we're going to get to this point here. If not nullables contain symbol, which is a funny way, I'm going to make a comment here because this doesn't quite read right. So if we've reached the last nullable non-terminal, so we're going to go down the line. This loop here actually iterates over the right hand side, but it only iterates up until the point that we hit a terminal. Yes, a terminal or a non-nullable non-terminal. You can work through the logic on your own on that, but yeah, so that is going to give us this top loop here explained is really this behavior of just walking down the line of each of the symbols until you either reach a terminal or you reach a non-nullable non-terminal. And you do that for every rule, which will eventually be unioned together to give you the full set of the first of whatever that non-terminal is. And so we can see if we kind of do the calculations on this, we have these two sets being unioned together. The first of D is X, and then unioning that with the singleton set Y, that gives us the expected answer that we have up there. At this point, we can get rid of those quotes. We do a similar thing for the first of B. And again, let's just go to the test code here. The first of B is going to be X and Y. Well, why is that? Well, that's because the first of B is going to consider just this rule, because that is the only rule that has B on the left-hand side. And we're going to start with the first symbol here. And we're going to see, oh, it is a non-terminal. And so for a non-terminal, the rule is that the first of B is the first of that non-terminal. There's no other rule, or there's no other symbols here, so we're done with that rule. There's no other rule. So this is a simple kind of recursive definition. First of B is the first of C. We already have first of C is defined up here. So the first of B is going to be X and Y. And then similarly, it's an identical process for calculating the first of A. The first of A, we're going to consider this rule. We're going to look at the first symbol. It's going to be a non-terminal, and so we're going to say that the first of A is the first of B, which again is the same set X comma Y. And sure enough, our first test here on line 273 says that it should be so. So that is the rule for firsts. The rule for follows. Let me check one thing real quick. Yeah, so that is the rules for firsts. We are going to look at another example here to calculate the follow sets. We are going to start off with the grammar. A goes to X. A can also be empty. B goes to A, Y, AX, and B goes to AY. And we want to calculate the follow sets of these things. So the follow set is a function, again, defined just like first on the set of non-terminals. The follow of a non-terminal is the set of terminals that can appear once you reduce on that. It's the set of symbols which, when you expand, will immediately follow that symbol. And so the way that we calculate follows is that rather than looking at the rules with the left-hand side equal to that symbol, we actually want to look on the right-hand side. We want to find all instances where we see this non-terminal, and then we actually want to look at the symbol directly next to it in line. So in this case, the follow of A is going to include X from sort of this situation up here, and include Y from this situation over here. And so our follow is going to be X and Y. For B, things are a little bit different. B can't actually appear, B doesn't appear anywhere in the right-hand sides of anything. Oh man, how does this work again? I feel like this should be the empty set. Is that correct? I should probably put this in my test. Sort of intuitively, B always has to be your start symbol. If you start with A, you'll either get the string X or you'll get the empty string, and that's obviously not going to allow you to ever get to a B. But whenever you have a B, that's sort of a top level symbol, so that nothing can follow. It's kind of like what can follow if you're going to write a programming language and you have a top level rule, a start rule called program, and maybe that's going to be a set of decals or something like that, and just keep it really simple. It's just like a sequence of decals, and decals is either going to be a decal followed by decals, or it's going to be empty. Like if this is your grammar here, then nothing can follow program, because the entire everything that you parse is part of that program, and there's nothing that follows it. The program spans the width of everything you parse. It's similar here. There's nothing that can follow B, because B is sort of the start production for everything. It doesn't have to be the start production, but if it wasn't, then it would be kind of pointless. So I'm just going to add that to my test here. I need to bring that symbol into play. And then we'll do that and make sure that our tests still pass. So that looks good. So that one is a little degenerate. The test here is really meant to be test follow. The test here is really meant to be on A more than anything else. Let's look at how we are going to work with test follow nullable, whatever this test was that I wrote up. So in this case, we have A goes to X, we have B goes to AY, we have B goes to A, C, Z, and we have C, it has an empty production. And so the interesting case here, according to my test, was actually what follow of A was supposed to be. So let's look at follow of A. So the algorithm that we've lined out is we're going to look at all of the appearances of that non-terminal among the right-hand sides of all the rules. We're going to look over at the next symbol over. If it's a terminal, then we're going to add it in. If it's a non-terminal, we have a different situation, because when we reach into the non-terminal, you can imagine the C is going to expand into something, and that expansion is going to start with some terminal. It's going to have a first set. So we actually would normally, we are going to do this in this case. It's a little bit of a bad example. The first is, or the follow is actually going to be the first of that non-terminal, because again, like kind of ignoring the fact that you can see this rule here, this C might expand. Like if we were to be a little myopic here, ignore all the other rules, we see this rule kind of in isolation. We see that C is a non-terminal. It's going to expand into something, and the first thing that's going to follow A is going to be, so that follow in some sense is like the first thing that follows A, and so you read it out in English and it kind of makes sense that whatever the first is of that non-terminal is going to be part of this set. But there's one other thing that we need to union in here, because C is nullable. And so in this case, if the symbol is nullable, we're going to just continue to walk down the line until we run into a non-nullable terminal, or a non-nullable non-terminal, or a terminal. Kind of similarly to the calculating the first sets, where you are going to walk down the line until you reach, from the start, until you reach a terminal or a non-nullable non-terminal. You're going to do the same thing here, where once you're going to continue down the line, and so we're actually going to also add Z here. The first of C in this case, we can calculate that based on what we knew before, or based on what we talked about just a second ago, and that's going to be empty. And then that means that follow A is going to be the set, X, it's going to be the set Y, Z, and because this unions with an empty set, that has no effect on it. And sure enough, that is our example. Our test case here is Y and Z. I feel like there should be another example here. We have a more complicated example. We'll just lean on this one. We'll go through this. So A is going to go to B, C, D. B is going to go to X. B can also be empty. C is going to go to Y. C can also be empty. D is going to go to empty as well. And E is going to go to A, Z. I don't know why I calculated the follow of B here. This seems kind of weird. The follow of B, maybe it doesn't make a difference. The follow of B in this case, we're going to go to this, say that follow of B is going to be the union of the following sets. It's going to be the first of C, union, well, C is nullable, and so therefore it's also going to be the first of D. But this case is also a little tricky, because when you get to the end, if you and the last symbol that you checked was also nullable, you're kind of tempted to ask, well, shouldn't it go beyond the end here? Because what if C and D were both empty, and we're trying to figure out what follows B? if C and D were both empty, it would be something that would follow whatever this string is here. It would be whatever the follow of A is. So there's a special case that you add in the end. We'll take a look at where that is in the code. That would be this case down here. That when you reach the end of a right-hand side of a rule using this method, and everything to the right of that symbol that you're considering is nullable, you actually kind of pop up the stack in a certain sense, and you have to union in the follow of the left-hand side, which in this case is A. So with that all said, let's just calculate this. Intuitively, the first of C has to be, is going to be Y. The first of D is actually going to be empty. And the follow of A, this is where we're going to we could do this one intuitively as well, but we might as well practice what the algorithm is. We'll start with follow of A. We're going to find all instances of A on the right-hand side, and we're going to look at the next symbol over. So this, we'll just go ahead and replace that with Z. So the total follow set of B altogether should be Y comma Z. Is that what our test case gives us? Y comma Z. Excellent. So let's look at this code a little bit more carefully. So to calculate the follows are firsts. What this is going to do is it's going to find all instances of the symbols on the right-hand side of the rule. What we're actually going to do is calculate them all at first, and so we're going to just iterate through all the symbols. That becomes the symbol that we're looking at that has a box around it. That's going to be symbol in the code. And we keep track of the index of it because we want to go down the line in order. So we're actually going to create, we're going to find the next symbol in order by taking its position, adding 1, and that becomes the index of the next rule, which we'll call follow. So follow is whatever the arrow on top is pointing at. If the follow is a non-terminal, then we're going to just add that to the set. And if it is a non-terminal, then we're going to add the first of it. And then that will just walk through the rest of the list. Once you get to, I feel like this logic can probably be combined, but maybe it was easier to do this way. But in any case, follows can also be follow. So this case down here, this for loop, encapsulates the logic that if you hit the end, and what we actually do is we're going to iterate through each of these backwards, looking for the first place where a non-nullable non-terminal is found. And so while we find that each of them is non-terminal, we're going to link it up. And then if it doesn't contain that, we're going to break. Yeah, hopefully this logic all works. There may be some corner case that is slightly off from what I was expecting, but we're going to just use it until we are proven that there is a bug. Is the way that it works sometimes if you're just doing hobby projects. So where do we want to go from here? Again, we've got a bunch of tests. The next element that I want to bring over from my previous example is are the items and item sets. And I don't know if I want these in the same file or in different files, but can I have to my thing or no? Whatever. So let us grab this. So in the context of grammars, we work with these things called items. And what an item is a rule together with a position. So an item is a way of telling you, in some loose sense, when you are focused on a particular rule, how far along have you parsed into that rule? So an example of an item, if you have a grammar that's like A goes to B, C, X, maybe you've, or let's do X, Y. Let's do something real simple, X, Y, Z. So this is our one rule grammar here. It's just the starting rule expands to X, Y, and Z. And now imagine that we start the machine up. The item is going to capture the idea that we're at this rule. We are trying to parse based on this rule, but we haven't consumed anything yet. So the dot here is kind of it acts a bit like a cursor. It tells us that we are at the start. We have not parsed X, we have not parsed Y, we have not parsed Z. Once we parse, or once we consume that X, then we are going to move the cursor over. And once we parse or consume the Y, we're going to grab that. And then once we consume a Z, we're going to have the dot at the end of our right-hand side here. And at this point, we have consumed all of the tokens necessary to perform a reduction and turn what's currently been the last 3 tokens that we've seen. We can turn that into an A. The way that we represent this is effectively the rule that we're going to work with, and then the position here is it's a number that tells you where it is. So if we have the dot at the very start here, it is right before the 0th element. If we have the dot is here, then we are at the first element. If we have the dot here, we are at the second element. If we have the dot at the end, we have the third. And so it's important that there is a constraint on this. The position must be between 0 and the length of the right-hand side, and that is inclusive. So you actually have one more position than you have slots on the right-hand side. You can go 0 through 3, which is in total 4 different values. And so let's go ahead and write some code for this. So one thing that we're going to add is an implementation for rule of G. We're going to have the ability to turn any rule into an item, and that's a very simple matter of taking the item, we're going to create an item using the self object as the rule and the position as the position. We also want to do an assertion on here for the sake of consistency that position must be less than or equal to self.rhs.len. Did I have, what else did I have in here? Let's write a debug instance for this. So for any lifetime G, stood fmt debug for item G. We are going to write the left-hand side for I in 0 self pose. We are going to write whatever the right-hand side is. We're going to do that again, starting at pose and ending at the length of the right-hand side. So these two things together are going to, and I'm going to put a space before here, these two things together will print out the space-separated right-hand side in total without missing any elements. But we're going to write it, break it up into two separate for loops here so we can sneak in the dot that we want to add. And so that gives us the ability to do something like foop. Let's grab a grammar, not a very long one. Let's grab a short one. Do I have the ability to grab a rule from the grammar? I'm not sure that I gave myself that. Impl grammar. Oh, I did. And we don't need this big of a grammar, we just need X, Y, Z. So we should have dot X, Y, Z. Is that going to work? The grammar is private. There we go. And then if we do that, and if we do that, we should get, we will go ahead and run it, and we will see that something is not happy. Where did I see that error? Item, oh, this should be a use. My syntax highlighting is broken. Or is it? Ooh, broken. No parser for the Rust language. Where did I put the parsers? Local, neovim. like share something. neovim lib nvim parser. Why do I need lib nvim? It's already in the neovim directory. Local neovim overwrite bash.io. What is it? It's rust.so. Okay. So I don't know if that actually made my highlighting work. It doesn't look like it's all that much better. But we can at least run our test. No method name. Len found for grammar symbol. Oh, whoops. That should be RHS. And on line 10. And on line 23, something's going on here. Oh, that probably needs to be a debug. Why didn't it put the spaces in there? We're going to write the left-hand side. Oh, so it didn't actually put the space in there. There we go. Unused results. And item foo failed. Oh, my assertion is bad. It's fine. Let's get rid of these warnings first. That's why. There's only 3 elements there, so that is expected. There we go. So we've got our tests for the debug. And then there's going to be a bunch of impl methods for items. We'll get the standard ones out of the way. For example, we just want accessors. For the rule, for the position. For the grammar. I forgot to put an accessor for the grammar on this. I don't think it hurts. Let's go ahead and just add that. And most of these are going to be copied over from the other one. I always wonder if this is the right way to do it, or if it would be better to make this a smart pointer style thing where it just automatically dereferences to a rule. But we'll just go ahead and do the left-hand side is a symbol, and we'll just these are very straightforward. Just pass through to the other side. It should be a vec. And then there's a couple of helper methods that are good to have on here. I define next symbol to be an option symbol, and that's going to be if self.pose is less than self.rhs.len. If we're at the end, we return none. Otherwise, we're going to return self.rhs, self.pose. And that in effect will give me the symbol following the dot. So in the case of I guess I don't actually print this out. In the case of this here, the next symbol will be some x, and this one it'll be some y, and for this one it will be none because the dot is at the end. So we've got the next symbol. The other method that we want to add, which is useful to have, is step, which will take the item and will just give me there's a better way to put this, self.rule dot item self.pose plus 1. There we go. So it's going to give me an item with the dot moved over one position. So in what I've written here, each one of these is actually the next step down. We'll go ahead and just write a nice little test for this. Step item. We will do item is the first rule dot item 0, and then we will do item, and then to make this you know what, we're not gonna push that off on the user. I'm going to change the API just a little bit up here so that step will actually give me an option. And we'll just copy the same logic down here. And that way we don't get a panic if you overstep your boundary. If you want the panic, you can unwrap it yourself. Otherwise, yeah, so that's a little bit nicer. We can do item equals item dot step dot step. And then the last one we want to do is item dot is finished. And we want to assert that item dot step is none. And then we can go ahead and we want to unwrap all these. Consider borrowing here. You know what, we can do this a little bit easier. Item. Consider borrowing here. Why? Item equals item dot unwrap. Expected item. Oh, why did I put an ampersand there? That shouldn't have been there. And then the last thing we need is finished. Which can just be the simple condition of is it equal to the length. think all of my tests pass. Okay, so we've got our item struct defined here. So the items are enough that you can actually start building a machine to do the LR parsing. The problem that you run into is that they're only really sufficient to create a non-deterministic state machine. And so that this is where there's so much hand waviness. There's one paper I found that explains it well. Let me see if I can't remember where it was. I can't remember. It was one of the papers on GLR parsing. And it was some... I can't remember where it is. So the items themselves are one ingredient. I'm going to hand wave this away, and we're just going to go ahead and throw this together, and we're going to hope that this is at least somewhat sensible in the end. An item set is actually going to be a collection of items. It's just going to be a standard set. Where is the item set definition here? I'm going to do pub struct item set tick G. And we're going to have the grammar again, tick G grammar. And then we're going to have a vector of items. So you're going to have a way to create the empty item set. Something I also found useful was to create a singleton set. That is an item set that contains a single element which you can create from an item. And the way that that works is very simply just grammar becomes the items grammar. What is the issue that we're running into here? Cannot return value referencing function parameter item. Oh, this is because item should be all the good stuff. It should be derive, clone, copy, partial. We're not going to get partial you can eat for free. Item is borrowed here. Returns a value referencing data owned by the current function. Item is borrowed here. I know item is borrowed there. nice item dropped. Oh, I bet I did a silly thing in my definition of grammar above. No? I don't need that. Okay. I did the same thing here, I bet. Yeah, there we go. So whenever you have these structs that own references, you always have to be careful when you are trying to project it, when you're trying to give access to it in a method, because this ampersand self, usually you want this to be not an arbitrary lifetime, because it's still going to have some kind of relationship to tick-g, but the ampersand here and the g over here, you don't want it to have to be borrowed for the entirety of the grammar. You want that item to be, or that reference to be dropped. So we won't worry too much about why that happened, but so we have these two methods here. We'll add a couple more. We'll do an is empty. And we're going to have a private function, insert. Do I need this? I don't think I need that. For search item, if search item is equal to item there. So you're going to make sure that the item is not there, and then you're going to do items push item and return true. So we can now add elements to the item set. We want to have a public function called items that will give us a copy of all of the items inside of here. So self.items.clone. And for convenience, we'll do grammar. Again, we want to make sure that we are going to give back a tick-g grammar, but the self parameter has an implicit lifetime. There we go. And so item, what is this? Search item? Item? What is my error here? Why does my LSP not work? This is where we need to implement for our item type. We have debug for it. We need to impl partial eq for item tick-g. And this is going to be similar to the partial equality for rule. So let's just grab it from there. Partial eq. It's literally going to be identical, except we're also going to have the condition that self dot position equals other dot position. And that's going to be the rule. Here this is we can do self dot rule equals other dot rule. There we go. So the rules have to be the same and their positions have to be the same, and then two items are the same. And then similarly, we can implement eq for the different items, and then everything is satisfied except for the fact that my stuff's never used. Okay, so that's all the boilerplate. The two methods that we actually need are going to be the following. They're going to be a little bit more intense. So let's go through this somewhat slowly. So we're going to have these items, and if I remember off the top of my head what the best example for this is, it's probably just as good as anything else. Let's work with an ambiguous grammar of expressions. We're going to have an expression. Well, let's not do it. Let's not use the ambiguous one. So an expression is going to be a term plus an expression. A term, oh, one other thing it could be, and let me be consistent about my notation here. So E is going to go to term plus an expression. An expression can also just go to a term. It doesn't make a difference. You can either kind of add things up as much as you want, or you can end with a term. And a term is going to be something that you're going to be able to take a factor and times it with another term. A term can also be just a factor. And a factor can be let's do X or Y. So this will give us a grammar that encodes the ability to say stuff. Oh, one other thing that we need, I forgot this is the most important one to make it nice and useful, is parentheses. We're going to say that a factor can start off with a parenthesis, and then it has an expression, and then it has a closed parenthesis, and now you can have arbitrarily nested arithmetic expressions with X plus Y times X plus Y, and this will parse according to the standard arithmetic. So what we're going to do here is we want to write we want to write our a machine that will parse these expressions. And so what we're going to do is designate the starting state is going to be, or the starting non-terminal is going to be a synthetic symbol. S goes to E. We're not actually going to store these as a non-terminal inside of our grammar, although in practice there's no harm in doing so. But all the presentations that I've seen will always treat the starting symbol in a special way, and it treats the end of stream symbol in kind of a funny way that I don't like. So we're going to kind of ignore that, but I don't know, we'll keep it in just because it'll make the presentation a little bit easier here. So the machine works based on the calculation of so-called item sets. And the first item set that we're going to always work with is based on the first rule and the 0th item there. So we're going to take the position marker and actually put it before the first element inside of the right hand side. The first is we're going to put it in front of all of the symbols on the right hand side. So from here, this is essentially equivalent to saying item sets : singleton on whatever the item, the rule 0 dot item 0, whatever. But from here, this is going to tell us something about the state that our parser is in. We're parsing the starting rule, we're parsing an S, and we haven't consumed anything yet. And we're going to calculate what's called the closure of this, and the closure is essentially going to figure out what are the other items you could get to by doing reductions. So what that means is the dot precedes E in the grammar. So this is the same state, effectively. We're going to take all of the rules that start with E. We're going to imagine expanding that E and putting the dot instead. We're going to take this item E to T plus E. put the dot in front there. And we're going to do the same thing with this rule e to t. We're going to take that and put the dot there. And then we're going to, again, calculating the closure, we need to add all of the t rules because there's now a dot in front of our t. So we're going to do t goes to f star t, and we're going to do t goes to f, and we're going to put the dot in front of all those. And we're going to go one last time. F goes to open parentheses, E, close parentheses, or it's going to be X, or it's going to be Y. So this is the closure of this singleton set. So we start off with this one, and these are all of the equivalent positions that we are in. And this item set is really important for working with our machine because this is the identity of the states in an LR0 parser. When you are creating an LR0 parser, you are in a giant machine, and you are always in one state, and the state that we start in is always the one that looks like how we've created this here. So let's go ahead and throw that together. How does that look? And the closure is something that we don't really need to be. We can make it pub. It's fine. Let non-terms added. So I had thrown this together with a hash set. And this is going to require an import. Let me write this exactly as I have it in my notes. So we are going to start off with keeping track of the non-terminals added. The item sets is going to contain. So we're going to start off with whatever the set of items are that we're working with, and from here we're going to go into a loop while my new items is vec. Item in item set. I'm going to go through all the items. If let sum symbol equals item dot next symbol I no longer remember how any of this works, so we're going to write it down and then try and reverse engineer it. and it looks like we had a little convenience function defined here. So let's go ahead and find our grammar methods. Do rules for we don't need a helper method for this. Do an into iter.filter rule.lhs equals symbol collect. We don't even need to collect it. We can just iterate over it. I have missed a closing thing here. There we go. Nope. Items. And where does this come from? Or item in new items. If not item set.contains item set.push item. Go ahead and just throw that in there. Okay, so everything's broken. I don't know what I'm doing. What are we doing here? So items added is true. Non-terminals added. Hash set symbol. Okay, that looks all good. Item set is a copy of all of the vectors. Okay, and that's just like what, clone? I can just clone that, can't I? Type annotation requires that item set is borrowed for G. Okay, I don't know what that means. So we are going to create new items, items added, false, item in item set. We're going to say if the symbol is non-terminal contains a symbol, we're going to insert it, symbol. We're going to iterate over these things, throw these things here, is borrowed after move. Where are we moving this? Okay. Oh, I bet my clone here. This is the back of an item of G. And that's going to be a reference to an item. Oh, move occurs because new items has type vec item. What did I do wrong here? Oh, is item being... Item is clone and copy. Borrow with moved value, new items. Oh, I bet it's because this is trying to infer the type in my original version. Item G. Type annotation requires that item set is borrowed for G. And maybe, nope, doesn't make a difference. Okay, where are we running into issues here then? Why does this version of the code work? Borrow of moved value, new items. For item and new items, oh, did I screwed this up, didn't I? This should probably be in the next block down. Maybe? I don't know. I have no idea what's going on here. One further than that? Okay, maybe that's what I did wrong. Just copied my code wrong. The issue here... Oh, wait. The issue here is I don't know what I'm doing. Well, I've wasted a lot of time with this. So what we're going to do is it's kind of fixed point algorithm. A fixed point algorithm is one where you iterate until things stop changing. And so here we're going to make use of this flag, items added true. This really, I don't like the way this is worded. We're just going to make this a while loop. And then we'll create a dirty flag here. So we are going to loop indefinitely, but then at the end, if not dirty, then we're going to break. So as soon as we get to the end of an iteration where nothing changed, we break. And the trick here is that as soon as you add an item, you're going to set the dirty flag. The item set here is meant to contain all of the items. Call this items, is meant to contain all of the items that we have accumulated so far. It's basically the final answer. The final set of items that we're working with. It's the closure. It is, we are building up the closure into this mutable array, and into this mutable vector. So we are going to create this temporary vector, new items. It's going to be also mutable. We're going to iterate through all of the items, but by doing this, we lock the original in place, and this is going to eventually come to augment items, because items is being iterated over. You don't want to end up with iterator invalidation, and so we're going to create this new space for new items to be placed. And then for each item, we look at the symbol, the next symbol. Again, we have this list of items like this. And we're going to look at the next symbol. That is, if the dot is here, we're going to look at E. If it's at the end, then that's why we have this if let sum. If we're at the end, then we don't actually go through this. But assuming that there is a symbol, if it is a non-terminal something special happens. We are going to first make sure that we have not added that before. So this non-terms added is going to be a hash set of all of the non-terminals that we have encountered in this fixed point operation. So it starts off empty, but because the dot is in front of an E, we're going to add E to this list of non-terms added, assuming that it doesn't already contain it. So we actually skip this. This is sort of an optimization. I don't know if you actually technically need it, but we're going to avoid considering ones that we've already considered. So at most, each non-terminal can be added once, and when it is added, we are going to grab the how do I do this? Come on, Ubuntu. When it is added, we are going to look through all of the rules where the left-hand side is that symbol. So here we're going to iterate through all the rules, and because we are looking to add in E, we're going to take these two rules and we're going to iterate over them. And for the first rule, we're going to create an item taking this, but we're gonna add the dot at the very start, which is item 0. And we're going to push that to the vector of new items, so that gets added. And then we set dirty equals true, and then we do it again because we're going to do it for both of those rules. And then we get to the end here. We do that for each of the items. We only had one item to start with. We've added these two rules to our these two items to our new items list. And now that we were done with that loop, with that for loop, we're going to go over each of the new items, and if the original set of items still up here didn't contain that particular item, we're going to push that item. We can't borrow items as mutable because of some reason. Cannot borrow items as mutable because it is also borrowed as immutable here. Feel like that's not the case. It should be dropping this reference. There should be no references to items at this point. Non-terminals added contains symbol. We're going to insert this symbol. Is this because I have forgotten to add partial equal, clone copy, like all the good stuff's here? Where's item actually used here again? Oh, wait a second. I guess we're shadowing here, but that shouldn't hurt anything. Items.push item on 205. I don't see where I'm making a borrow against item here. In fact, let's call it some dumb name. Oh, that's what I did. Okay, I played this game against myself again. That don't add lifetime parameters willy-nilly to self, because that's not the correct way to use it. Okay, that makes more sense. All right. All right, that was so obnoxious to debug. So anyway, we calculate the closure of the items here. Oh, that was painful. All right. So the last method that we're going to add is something called follow. We're going to have symbol is symbol tick G, and that's going to return an item set. So this is going to be the main workhorse for creating new states in our state machine. Do I need that clone there? I don't think I need that clone there. But I do probably need to have... no. So we do that. And then after the for loop, we're going to let item set is going to be an item set with grammar as self.grammar and items given above. And then finally we're going to do item set dot closure what is this option item nonsense here? Dot step so this unwrap here. So what are we doing here? Well, let's get the picture, and then we will validate that what I have here makes sense. So given this state, we want to generate the next state, the next item set based on this item set. And the way that we do that is we're going to follow a certain symbol. So we're going to, the transition from that state based on the symbol E, let's say, is going to look like this. We're going to take, let's not draw that big, it's not going to be that big. We're going to take each of the items in our item set. That's this for loop here. We're going to look at the next symbol, if there is one. So here is E, here is T, here is T, here is F, here is F, here's open parentheses, X and Y. If the next symbol exists, that's what this sum is, and it's equivalent to the transition symbol that we're working with here. We're going to do an items.push. We're going to keep that item, but we're going to step it. And so what that means is that we are going to take this item. We see that the next item, the next symbol in line is the E, and so we're going to step over the E. And for any item inside of our item set where the next symbol is not, we just drop it. And any symbol, we don't have any here, but if the symbol is at the end, we drop it. So if we did a follow E on here again, here we only have the one item in our item set. Because we're at the end, this if let sum never triggers, and therefore this is going to be an empty item set with no items inside of it. On the other hand, if we take this state here and we are going to transition by X, we are going to, like, all of these will fall off, but we get this one where we see F goes to X dot, like that. And let's, just for one more example here, if we transition by T, what happens is the first one falls off, the next two will stay on, and then the rest will fall off. We're going to take that E, the dot moves over, so T dot plus E, and then the other one is E arrow T dot, and that is going to be our other state. So that is going to be the general strategy for starting with one of our states and then expanding it to be as many states as we want. So that's the follow algorithm here. Make sure, what did I run into? There's some type error, and I just mistyped. And so I'm not sure I'm going to take the time to write out our tests at this point. So we're just going to leave it there. Add all of our code. Make sure our tests still run. And what happened here? Okay, we will, oh, I don't have an upstream. We will, well, let's go ahead and create that now. So GitHub. What's the import repository button do? Does that do what I want it to? Nope. New repository, grammar utils. So let's make sure that crates.io doesn't already have a grammar utils. Okay, we'll just go ahead and hope that that name stays available. We'll go ahead and add our remote. And of course, we're going to suffer the fact that it's going to recommend using HTTPS instead of SSH. And we can push. And here is the start of our grammar utils repository. Until next time.